Okay. So this is the last day. I thought, well, originally the bonus we taught. So let's try to recall where we're at. It's in the proof. So Dennis explained yesterday that we have an equivalence between the sheaves like D upon GI, so that's a subcategory of sheaves coming from Eisenstein series, and the analogous between category of spectral type. And this was essentially the constant that the Langlands functor created with a constant term in Eisenstein. And so that leaves the question of the cusp part. So we have to say something about functor from cusp-ability modules, which goes into positive layer sheaves on stackably reducible local systems. And what are we going to say today? The goal of today, so let's give this a name. Let's call this LG cusp. The goal is to prove that LG cusp is conservative. Conservative meaning if it kills an object, then the object was zero. Okay. In fact, we'll do something slightly stronger. Well, in fact, we'll prove that the entire assembly functor, the LG temp, going from the assembly category to positive variant sheaves of losses is conservative. This is stronger because I think we've stated before that cusp-ability modules are template, although I won't use in the proof. But this is what we really need to prove. Okay. And so some remarks right away. So this is an important step for various reasons. One way to phrase it is to say that to prove the geometric Langlands conjecture from there, it remains to show that the left adjoint to the tempered functor is fully favored. The left adjoint is the functor acting on the functor relation. Yeah. So this will kind of be the work that remains after this talk.
You can also say that LG, so LG cusp is fully fixed.
Yes. Okay, and another remark is that.
And stand over because rewind for a second. But you're saying there's the thing that cusp-ability implies tempered. So this is a theorem scenario where I'll give a really nice geometric proof of this, but also if you just want like a happy proof, then we do have the ingredients for some thing.
Yeah.
So I don't know if we can say it out loud.
I can say it out loud. So yeah, so we saw yesterday that cusp openings, they're supported in a strong sense in a positive convex open. And well, there's a statement here that in fact anything that's star pushed forward from a positive convex open, so that includes cusp-ability modules, lies in the localization function from the Casanusti category. And we've seen that the Casanusti category itself is tempered. Anything in the English is tempered. That's the hacky way. That proof of Geraldo uses a characterization of temperedness that we haven't discussed, so. The second remark is to say that the proof will give above, will be above proof against sensitivity is it's different in nature from what we've seen so far, so it's micro-local in nature. The precise sense we'll see. So it does not use representation theory. It might use that as a reduction step to nil-point modules, but what is improved is really different. Any questions about these? Okay. So the first thing we'll do is reduce to this restricted situation that I talked about on Monday, where you consider nil-potent P modules with nil potency that support instead of all of them. That's the thing that allows you to tap into things like micro-local states. So let's see this. So the claim is that it suffices to show that the functor of LG temp when restricted to the category of P modules with nil potency that support. So this goes also into quasi-coherent sheets on locuses, but slightly better quasi-coherent sheets when this locus restricted, which was introduced on Monday. I'll recap some of the properties. It won't be so important, so I won't talk too much about it, but just this is kind of the target category at least first pass. This is the claim. Let's see the proof of the claim. In the benefit explain this to some effect, let me just kind of reset it again. Sorry, reset. Claim is if you prove conservativity in a smaller category, you also get it on the larger for all fields. So the proof of this is the feature of locuses restricted we're using is that it's surjective on K point when it maps to locuses. You're given some D module 1G, there exists some K point such that when you tamper with that, then will be corresponding delta sheet. This is nonsense. Slight lie, but let me kind of really you should take this to be kind of this could be an arbitrary field value, but let me take it to be the ground rule. Okay. So we've seen that sigma being a K point factors through logs as restricted. So the D module here really lies in E1G tensor over glucose, which I think I stated on Monday, but this is exactly the category of D minus 1.2 with no point singular support. Big clear about it paper. That you take as an important input to this thing.
What do you make sigma tensor, right?
Yeah, so this is acting by the corresponding delta sheet. This is a question we're going to sheet on locuses. That category acts in DM20, and that's what I mean. So if if this tempered Langlands functor is non-zero on this B module, non-zero, well, this is sigma and 0%. Then this thing has to be. So that's the reduction.
No, so I think the logic is very. You want to show that L is non-zero, right?
Yes.
So what you're assuming is that it happens on the golden symbols forecast, right? So like you assert that it's the same, but you don't know. Yeah.
So yeah, so no, it's a slight line. Maybe that's what you're alluding to.
No. I think the logic is okay, just say the logic again.
Okay. So you start with the d mod on 1G, so really be tempered. Okay, and we want to prove it's when you apply LG tech to it, it's not zero.
Correct.
And the logic was do some sigma such as sigma tensor f is not zero. Use that this is nilpotent to conclude that this is non-zero. That's sigma tensor this thing so that.
Oh yeah, sorry. Yes, yeah.
Okay. Any questions about this reduction stuff? Okay. So we're reduced to D modules on 1D with nilpotent singular point. And what we'll do is we're going to explicitly describe or characterize the kernel of the functor L210 and D nil and G to bicycle derivations and losses. Okay. In the following, so explicit here means in some kind of micro local sense. So to describe that, let's review a bit of the lead theory. Definition. An element in the dual Lie algebra is, which I kind of identify with G, is regular if the centralizer of an element is minimal. It's minimal dimension. In which case it equals the rank of G. Let me give another way to characterize regularity that will be a bit more relevant for us. So better for us is the following. Let's say we fix some non-degenerate character psi in the dual to n, the nilpotent radical of the Borel. And consider G star mod n, which we'll kind of think of as G star mod T base changed to point mod n. Then define the constant section as sitting in a Cartesian diagram we'll have the constant section mapping to G star mod n. This will map to n star mod n. And we'll have a point psi here. We have this diagram, and we'll take that fiber squared. Declare that to be the constant section. Complaint?
If you want to start in the thermodynamics, otherwise constant section would be static.
It will be f plus b mod n.
Or cost section 6 square. So
It's constant section is its own lowered.
but it's a subset of what? G star with that or G?
I don't want to consider it a subset. You can identify it with a subset of G star if you will, but I want to.
Great, plus B mod n.
I'm going to, but I want to address the complaint first. Okay.
Can you clarify what psi mod n is? Can
Say again?
you clarify what psi mod n is?
Yeah, so this is, and I'm just saying that the action of n on n star fixes psi being a character. This is the condition of psi being a character. So okay, to meet Sam's suggestion, so I'm setting things up that will be easier in the global case, but it will be a little bit weird now. So if we identify G star with G and N star with N minus, such that psi corresponds to some element F, then the constant section gets identified with F plus B modulo N, which maybe this is what Dennis you mean. This can be identified with F plus the centralizer of some E if you choose some SL2 triple container. This is kind of what I've done. It's okay.
So is it still just the companion matrix?
Yeah, exactly. Yeah, so one thing is that the map F plus B mod n to the regular elements 1G is a bijection of K points. So that's the point is this is one way you can think about regularity is that we're kind of containing some buffers. We're seen by some. Okay, so let's do this globally now. Oh, maybe first actually let me into the notation. So let's define G irrec to be the irregular elements. That's just the non-regular elements. And let's define N irrec to be the nilpotent and irregular elements. Now let's do it globally. For define nil irrec, it's a closed subset of the potential bundle of 1G to be the pairs of, we've seen that the potential bundle of 1G classifies paired with a G bundle and a Higgs field.
Above, you think that's the non-homogeneous character of one particular regular element. You just comment on why I'm breaking up the photo going for like just regular part. You know, it's just the one for this.
That's kind of the statement. If you take this slice and you hit it with G, you get all of it.
We'll make it compact for you.
Um, yeah, so you have some constant section, you can move it around with G, you'll get all regular. Define nil direct to be the pairs of G1 of the Higgs field such that phi is nilpotent irregular. So i.e. locally that goes through an array.
It gives a deeper remarks that we
Okay.
never actually said that. What did we have? Potential reference to Bungie are exactly these patterns.
So you want that?
So you what?
You want me to do that?
Just at least to say.
Okay, granted. Okay.
You did it very briefly when you calculate.
This can be the remark for it. So we saw that the tangent complex at a point PG upon G. This was the cohomology x of GPT by 1. And so dualizing using shared gravity you'll get that the cotangent complex x0 of it is exactly this vector space. Okay. And maybe we saw this in the first day.
Yes, but that we saw.
This is all.
First lecture.
Okay. Okay, so we've defined this closed subset is that the consecutive bundle of 20, and this will play an important role. Let's see exactly how now. The theorem A. We have an identification between this kernel of LG temp restricted to nilpotent E modules and the category of E modules whose singular support is contained in this nilp array. Okay. So here's an explicit characterization of when you're killed by the Langlands functor. It's purely in terms of singular support.
You can here ask what that theorem means for PGL2.
For PGL2. Okay, well, I'll do that in a second. So theorem B. I think Kabir asked that. It definitely could. Theorem B says that if you take the tempered things, so now we have to. The goal was to prove that this thing is never in the kernel. So we need to show that when you intersect with the rec, you get 0. Okay. In fact, it proves something strong, or we prove that this is really right orthogonal to this thing in some sense. Well, it's right orthogonal to this thing, not just that it's intersection. So I'm doing the PGL2 thing now, but okay.
Theorem A, this Langlands functor is the restricted version, because otherwise we wouldn't get it done.
It doesn't matter. So you can consider the target to be Foucault-Lux is restricted. The answer is yes, but also the functor hasn't. That's the same functor as including into DF1. one G and then mapping the usual Langlands functor, the kernel will say.
In other words, at the level of categories, Q co exists restricted is contained in Q co exists. And if you take the Langlands functor on this D node, then it maps into that subcategory.
But by the way, I can see how can the Langlands functor will be a quiz.
Well, but not on the temporary.
This is the tempered Langlands functor. So this is the one whose target is Q co instead of 8 co.
I will call it coarse, just to be precise, because it's, you are applying it to all demorphic, right, not just kind of one, but.
Oh, this is a typo. Thank you. Yeah, absolutely. Absolutely.
The temperate, you're applying it to everything.
Yeah.
But the target is probably close.
That's right. So this is the coarse functor. That was a typo. Any more questions? Okay, to meet the Beer's question, let's do Beagle PGL 2 and see what this thing is. So in this case, nil direct is 0. Isn't it easy to do SL2? I think SL2 is one easier. And I want one G to be simply connected. SL2. Here, nil direct is a zero function. And so we nil direct 1G. This is the category of E modules on 1G, such that each cohomology is a union of vector bundle plus connection. Whenever you take each cohomology in a coherent sub E module, it's a vector bundle with the connection. Oh, coherent. So in this situation, we're saying that the coarse Langlands functor, when restricted to d point G nil, the kernel is exactly those whose cohomologies are. Oh, sorry, we're more precise. Actually, this is extensions of just the constant sheet. Yeah, there kind of no non-trivial. The kernel of those for each cohomology, it's kind of a union of the constant sheet. Okay. The which thing becomes yeah, I think this can kind of be proven directly in this case, this one not so much. Well, okay. Any more questions?
Yes, this thing. A little confusing to people, like there's some version of it that's like representation from identity GL2 then a little version.
Yeah, I'm gonna say more about that.
Great.
Kind of well, that story, I don't know. This story is not good. Alright, I'm gonna say more about it.
In this example, what is the tempered condition explicitly?
The tempered condition is being left orthogonal to the, not quite being left orthogonal. It's very, very close to being left orthogonal to omega, i.e. having compact cohomology matching. Not quite.
So is this a counter from the 1G to logic or balance to G trap or balance to G trap instead?
It's really to Lotus G-check restricted. And if you then further compose with the map from Lotus restricted to Lotus, you'll recover. There's a diagram. Function maps. This is why I haven't really specified what I mean by this particular functor, because the assertion is that this functor here, or that is just including into the G and applying the usual Langlands function. And then there's an assertion which I haven't said, so that this is a force of character. Yeah. Yeah. Is that okay? Alright. Yeah. So let's do theorem A. I won't really talk about theorem B, but mostly about theorem A, because that's where the kind of most of the content is. So the entire analysis stems from everything stems from considering the functor of cos 0. The cos 0, I'll remind this was a functor from v of 1g. Select. The defining property, the main property was that it was given by the composition of the Langlands functor and then global sections. Let me just remind quickly how this was kind of given explicitly. So we had a diagram on n omega and a character down to A1. This map to 1G. And then cos 0 was given by you pull back to 1n omega. And then you integrate along the character set. This was the explicit formula, if you will. So let me cite some theorems. Theorem 1a is that this cos 0, when restricted to the nilpotent category, satisfies some very nice properties. Satisfies firstly that it's C exact. Up to some shift we will ignore. It commutes with word duality. And thirdly, there's an index formula, meaning the following. So if you have some well-known sheaf, say in the heart, we can explicitly count. So we know that when you apply cos 0, you'll get a vector space at degree 0. And we can explicitly calculate its dimension. So the dimension will be, oh, there's something I haven't said. Let me state it and then say the words I need to say. The dimension is given by the multiplicity of some specific connected component in the global nilpotent cone, which I call nil cos. We want to find that now. Right now, there's some favorite component inside the global nilpotent cone. We're flying in terms of this global cosine section, and which I'll define in a second, having this property.
I think Gurgen wants to ask what is CC.
CC. Okay. Well, is computer okay with if I say it out loud, or should I write something more?
I defer to Dennis.
Okay. Yeah. Okay. I'll say it out loud. So we've talked about singular support. This was you took some good filtration on your D module, and you looked at the support of the associated gradient inside the cotangent bundle. There is a more refined invariance, namely, if you look at the support, you can assign just a multiplicity, non-negative integer, to each irreducible component of that support. Look at the rank at the generic point of each component. This will also be independent of filtration and so on. That'll give you kind of a cycle inside the both the characteristics are. Any more questions about the theorem? I'll define no cos now. But...
Actually, I have another super deep question. So I got two separate keys for the Brady duality. So in order to take the Brady tool of the first sheet, what didn't you think the Brady tool of the other thing? Like,
yeah, so I mean, I guess an implicit assertion is that for zero evaluated to some construct. I mean, for hearing E module to open to its board, that define application. Let's define this nil cos. Yeah, so okay, so defining nil cos. So we have this character psi defining omega. This gives us a section of the cotangent bundle. One and omega mapped to its cotangent bundle. Well, we'll just define. So let's define the global cosmos section in a similar way. Find both sides of the globe by the same requirement as so we're on the board. By sitting in the following Cartesian diagram. So here we have the cotangent bundle of line G, and the global version of G star mod G. But then you need to phase change to G star mod N. So we do this. Omega. This maps by the codifferential to T star 1 omega. And here we have the differential. Okay. There's a teaching diagram like this. And these Stockton sections, they have the key property we'll use is certain transversality property to the nilpotent code state. So the properties of these Stockton sections. First, in the finite dimensional case, we take the finite product of cosine with G star mod G with a nilpotent cone. We just get the point it's at that. Even as the life size. And similarly for the global cosine slice, we will take the final product of G star upon G with the nilpotent cone. This intersection is just a single point, even though. Okay. And so now let's define little cos to be the irreducible component, the smooth point of node. The irreducible component containing this single function. Okay. That finishes the definition of cusp. Any questions about the theorem?
The connection might be is to say for us two always like how cost low looks like.
Cusp flow.
And no, and no.
I know.
Sorry, can I ask you a question about the capacity? So, you're saying that there's a unique irreducible component in the X flow.
Yeah.
And, how does it follow from the property?
Well, I'm just saying I've defined for you a favorite point in the node. And it told you it was smooth. It tells you there's a unique reducible component containing. But yeah, so the key properties kind of goes into the proof of it. I'm running very well. Okay, SO2.
What is emoji? What is inside you?
Say again?
Emoji.
Yeah.
What is inside you?
Yeah, so and this is like G star. Chosen the killing forms that in like G with G star, say.
There are two M's in way.
Okay.
The straight and the curl with A. That's the curl.
Oh, this is the notebook we following the file. That's the question? Okay. So we know we need the global notebook count and we study. Okay, SO2. So what does the notebook count look like in this case? Global notebook count. It looks like a union of positive integers. Okay, I'm kind of let's see. 1 minus G, 2 minus 2G, little p, the closure of these things. I'll tell you what these things are now. So now p, this is can be identified with like door exact sequences like so, plus a map from L dual to L tensor omega. From here you get a nilpotent Higgs field by adding E to L dual on phi. Like so. So that's a Higgs field. And
Normally this P would be non-zero.
yes.
But then you're not a zero section. Because you didn't say.
Okay.
Was it dependent on deep?
Depend on what?
That should be a deep.
Well, thank you. The degree of yeah. Degree of L. Maybe L to one.
Technically, you can ignore whatever the inequality is. The union of these components, but some of them are factors, so.
Okay, great. Yeah. So if I start from below, and then we'll be and milk toast is the bottom one. So let's probably keep those two here. So milk 1 minus T here, 2 minus 2G is the cosine one. Yeah, so the degrees will be such that this is necessarily isomorphism. They will have the same degree. It's the way to check whether it's 1 minus 3 or it's not.
You can write F work.
What?
Write F work.
Oh, yeah, okay. The F log in this case. What is this? So as a bundle, it's omega to the 1/2, so we chose a square root. And phi is the Well, I need to tell you how to give a map from omega 1/2 to this thing 10 to omega. So this is omega to the 1/2, so x on omega 3/2, and it's what, 0, 0, 1, 0, let's see. No dt. Right. Okay. What? This is a set theoretic view. So this node D embed locally closed into node. And okay, these are not locally closed inside of node. You can check the.
We are trying to understand what the restrictions of the D module and equivalent support. So this is a set theoretic restriction. You have a Lagrangian thing sitting inside the Lagrangian particle. And this Lagrangian splits into a bunch of irreducible components. So we ask, how can a Higgs field be nilpotent? There are two ways. Either it's zero everywhere, or if it's not zero, then it will be generically regular nilpotent, but it can still be zero at some point with some multiplicities. So there is a component where the Higgs field is never zero. That's the first. Then there are components where it's not zero generically, but it still vanishes with the bi with certain multiplicity. Those are the other.
All the groups is like, the new pulse is like locus work at every point of the curve. The regular limitation. Generates.
Yeah, so I should say this component of codes that consist of a set Higgs fields that are everywhere regular. They don't have finitely many points in the curve where they hit some regular no problem. All right. So theorem 2A does the following. If you have some E module with no point singular support in 1G, such that its singular support is not contained in this stack of the regular nilpotent bundles, then you can force it to hit the custom component. Then there exists, let's say, some dominant coed such that when you hit F with the corresponding egg operator, the singular support of this G will contain the custom component. It's sufficient just to hit because it's in reading material.
Why are we having a single
Why are we talking about a single Higgs operator as opposed to Ron or something?
Yeah, you said it.
Second?
There's a point.
There's a point, okay, so yeah. Okay. Well, that's. For any X, you can fix X theorem, and then there's some down for it. So yeah, that's a feature of it is that in this restricted setting, Higgs operators are at a point are kind of enough to see.
So on the first fix exit, and then there's something else.
I think you want to say that every F there exists a bunch of points with a bunch of Fourier.
No, I don't mean fix X is nice. So then theorem comes. It says that if you have a G module with abundance here support, you can find some co-weights such a blah blah blah. I really mean this. No. I fixed X. So you look very.
Dennis, it's geometrically, it's because like looks as restricted is essentially affine mod G.
Yeah. Yeah, maybe on the spectral side, it's not true that global sections on locus restricted is conservative. However, just fix a point, and then it will be true that you can hit like you can censor with a vector particle at some lambda, and check, and then global section by global.
I mean, let's say behind this discussion, as I understand Dennis's confusion, the confusion comes from the following point. Like we know that when you like, let's look at the example of SL2. If you are not on the zero section, you are somewhere on this new piece, on one of these new D bars. So you have a somewhere you have a Higgs field that's regular generically, and then there's a divisor where it matches. So if this divisor happens to be empty, you are already on course, you are done. Now, if this divisor is not empty, then somehow the most obvious, geometrically, the most obvious thing to do would be to say, let's consider the points where the divisor sits and apply the Hecke operators prescribed by the multiplicities, and then we prove that this will end on course. Right. And so, and this will probably be enough for your purpose. Since you don't, you would have a bunch of Hecke operators sitting in different forms. On the other hand, because of the fact that the singular support of a D module is always Lagrangian, such this cannot happen at a single point. It's like the entire if a point is included in singular support, then the entire component is included in singular support. So you don't have to worry about like I think from this point of view, the claim is that somewhere on the singular support you can find a point where the divisor just sits. The divisor is supported. Yes, I see that.
Maybe also remark this is not it's not important that you can find only restrict yourself to only one X.
Right.
Also, is it right that this kind of not very thing?
This is not enough.
That's kind of also help you use not in the way of
Yes, that's part of it, yes.
Yeah. Yeah, maybe just that this theorem uses suitable. Well, uses this theory of the converse to this not really thing. Yeah. Maybe one thing I'd like to say is, so we'll finish up the proof of theorem A now, but to answer Gubier's earlier question about this theorem here, here's an exercise. Which says that formulate and prove a analogous result for the category of D modules on G mod G with nilpotent singular support using the Fourier transform on G. So doing this, you'll see why this key property comes up, transversality condition, and but generalizing this is very. Okay. So now where are we? We want to prove theorem A, and so let's just see that theorem 1A and 2A implies theorem A. So what was theorem A again? This is the assertion that D nil direct on G. This is the kernel of the course functor restricted to D nil. let's prove this conclusion. So if you're given some E module with irregular nilpotent singular support, we get that applying curve 0 to any Hecke functor acted on F is 0. This is because this category is actually Hecke stable. It's the conversion of the Natalie theorem. And we've seen by theorem 1a that, but then if you don't meet the constant section, you're automatically 0. The T exact in each dimension is 0. So what does this mean? Concretely, this means that when you take LG course F, so this is a quasi-coherent sheaf on locus restricted. Whenever you tensor with vector bundle, the Hecke operator on the spectral flag, you just tensor with the vector bundle associated with lambda check and X. This is 0 for all lambda check. But this implies, I'll just say that this implies that the quasi-coherent sheaf itself is 0. This is what we said out loud before. Maybe I should say because part of the geometry here is that when you kind of rigidify, so you base change modulo PG check to point, this is basically affine. It's a formal affine scheme. In particular, quasi-coherent sheaves on this is conservative, meaning if this global section is trivial for all lambda check has some fixed point, then the sheaf itself is 0.
To show that the coefficient is 0, use the third property of this.
So this thing here, this was 1a.
And how? So you need to this multiplicity. Why is it here?
Yeah, so maybe this is a key point, so maybe I should specify. But consider this sheet here. This still has nilpotent irregular singular support. So this tells you that when you apply curve 0, let's check that so that you get some vector space. Let's check that each cohomology is 0. Combining 1 and 3, forget 2 for a second. Combining 1 and 3, it tells you that each cohomology, its dimension is 0. Because the characteristic cycle doesn't meet the custom component at all in this case.
So there is a consequence of 1a, which is the only thing we're using. But the consequence is that coef 0 on d nil, coef 0 vanishes if and only if the constant component does not appear in the singular circle. And this is tested. This is proved from theorem 1a by looking at Kleen's degree by figure, which is it's valued by 1, and 3 tells you what happens in each degree.
Okay.
Wait, can you say a word to me? You think that nil irregular is you say a word when people apply it.
At the end of the day, it's because these Hecke operators are given by some kind of smooth pull, proper push. Not quite true. Essentially it. Okay, I shouldn't. This was proven in a paper of Natalie and Newton for the nilpotent singular support. There, but that's the kind of geometry that happens.
You could maybe one word about it. It's like, okay, first of all, the general statement is true for any G invariant conical subset of the Lie algebra. And roughly the idea is like, suppose you have nilpotent regular singular support, that's something which is true at every single point. And now this Hecke thing is some kind of modification that happens at a single point. And so to say, it doesn't want to change the property of having the regular nilpotent single support at every other point, but that's a closed condition. That's a little like, maybe a heuristic for evidence.
Well, also you have to say that like, I could. Greater than both property put forward, and therefore we can control what happens.
That's what Joakim said. Joakim said exactly that.
At least supplement all this with more, even more stupid thing, at least like picture with tangent. Primary things, or it's in Fourier transform, convolution becomes point when multiplication after Fourier.
Oops. That's no good. I mean, I don't know what it meant, but that's,
Okay, if that is not helpful, like, yes.
While we're talking, I spaced out for a second, and there's a C in quotation marks that I don't know what.
This is containment. So now comes the other one. Okay. So, okay, we did one. Let's do the other. So, and then we'll be out of time, right? Somebody, oh, I'm already way out of time. Okay, so given F and this column, we want to show it has nilpotent irregular singular support. So what this tells you is that global sections of like what I call it E lambda. Yeah. E lambda check X times LG course of F is 0. We're all going to check. This thing here is cos 0 of the Hackett functor plus F. And so by theorem 2A, it must have irregular nilpotent singular support, because if it didn't, you could find some Hackett functor such that this guy has generically irregular hits the custom component, and then cos 0 of that will not vanish by theorem 1A. This is QED.
so you can, like,
Okay.
the reason we have like 45 minutes for Q&A is to take us.
Okay. Well, I think I'm almost
Done with 2, right? Oh, with A.
I'm done with A. Yes, but I'm not planning to say. I just want to say how A and B combine to give the main pair. But we've kind of seen that already. So theorem A and theorem B was theorem B on the board. It's not on the board. So this thing said that the only things tempered things cannot have nilpotent irregular singular support. So these two things together give you that the kernel of LG course when restricted to D nil is exactly the ones with, sorry, it's exactly the tempered ones. No, not quite what it gives you, is it? I guess it gives intersection of 0. Yeah, that's what I want. With D nil. Is 0. And this is the statement that the course functor when restricted to the nilpotent category is conservative on the tempered. Well, but this is what I want to say.
But you're not planning to talk about theorem B.
No, it wasn't.
So maybe we will have a Q&A before lunch.
Mhm.
Maybe either you or Rubio can say something about like along the lines of theorem B.
I can say yeah, I can say a few words about it.
Yeah.
So when was this?
Then when would it be?
Yes,
After my talk before lunch.
Okay.
This time.
that's fine.
so you can prepare something labels.
Yeah.